When we think of distance, what probably comes to mind is how far away something is from another thing, like the distance from your house to the mall, for instance. In mathematics, however, the proper definition of distance is simply the length of the shortest straight path between 2 points. It is important to note that distance is a scalar quantity and not a vector quantity, meaning that it only has magnitude and has no direction. Now that we've established what mathematical distance is, let's move on to understanding and working with different situations regarding distance.
First of all, let's take a look at the distance between 2 points. Here we have an xy plane. Let 2 points on the plane be A 2, 4 and B negative 3, 6. So what is the distance between them? Recall that distance is the shortest straight line path between 2 points. Hence we connect A and B with the straight line. We can call this line AB. As such, the distance between AB will simply be the length of the line AB. Now let's move on to looking at the distance between a point and a line. Let's say we have a point C and a line L. So what will be the distance between them? Once again, let's recall that distance is the shortest straight line path. One important thing to note is that for lines, the shortest straight line path will always be a normal to that line. Hence, the distance between point C and line L will not be this or this, but this. A line that joins the point to the line which is normal to the line. This means that the angle between the normal and the line is exactly 90 degrees. Then how do we calculate the distance, which is the length of this line? Let's put point C and line L into a Cartesian plane. Point C has coordinates 5, 7 and the line has an equation of xy equals 0, negative 1 plus t 2, 1. In order to calculate the distance between them, firstly, we need to find any one point which lies on the line. From the given vector equation, this information is easy to find. A point on the line is simply 0, negative 1. Let's call this point D and draw a vector between this point and point C. We can call this CD. Using vector subtraction, we know that vector CD is negative 5, negative 8. Next, we will need to find a normal to the line. This can be done using the line's direction vector. A vector normal to the line will also be normal to the line's direction vector. As such, we have to find a vector whose angle is exactly 90 degrees to the direction vector. From the given vector equation, we know that the direction vector is 2, 1. One way to find a normal vector is to use the dot product. Remember that the dot product between two normal vectors will be 0. As such, we can use trial and error to find the normal. For instance, negative 1, 2 is a normal vector n. However, there is a second way to find the normal. All we have to do is take the x value and y value of the direction vector and switch them. Then, a negative sign is added to one of the values. This is a shortcut to finding the normal vector of a line in 2 dimensions. Now that we have vector CD and vector n, we can calculate the distance between the point and the line. To do this, we will use vector projection. In this case, we are projecting vector CD onto vector n. But what exactly is vector projection? Well, when you project one vector on another vector, it's like using a torchlight and shining it over the first vector, so that its shadow will be cast upon the other vector, and we will get this vector. If we are projecting CD onto n, it would be written like this. However, in this case, we are calculating the magnitude of this vector, so modulus is added to either side of the projection. Then the formula of projection will be this: the dot product of CD and n over the magnitude of n. Don't forget to add the modulus. Now let's apply the newly learned formula. The projection of CD onto n will be the dot product of negative 5, 8 and negative 1, 2 over the magnitude of n, negative 1, 2. The numerator will be the sum of negative 5 times negative 1 with 8 times 2. Then the denominator will be the square root of negative 1 squared plus 2 squared. Solving this, we would get 21 over the square root of 5. So in decimal form, the distance between the point C and line L is approximately 9.4 units.
Moving on, let's now look at the distance between two lines in two dimensions, also known as R2. Before moving on to considering the distance, we must first consider the possible situation of two lines in a plane. Firstly, two lines will either be parallel or non-parallel. We know that two lines are parallel if their direction vectors are parallel, collinear, or scalar multiples of each other. If the two lines are parallel, then only two situations are possible. The lines will either be parallel and distinct or parallel and coincident. The difference between these two cases is that two distinct lines share absolutely nothing, whereas two coincident lines share everything. However, if lines are non-parallel, then they will intersect at a point. This is always true in R2. As long as the direction vectors of two lines are not collinear, then the two lines will intersect. Now, recall once again that distance is the shortest straight line path between two things. Let's evaluate the distance between two lines in each of these three cases. A. If the two lines are parallel and distinct, then the distance between them will be a line like this, which is normal to both lines. B. If the two lines are parallel and coincident, there is no distance between them because they share all their points. The distance between them is 0. If the two lines are non-parallel, they are intersect. There is no difference between them because the shortest path between them will be at the intersection point. The distance between them is 0. Hence, we can only calculate the distance between two lines if they are both parallel and distinct. Let's take a look at an example of the distance between two such lines. Let line L1 be xy equals to 0 minus 1 plus t21 and line L2 be xy equals 37 plus t21. Given that the two lines are parallel and distinct, what is the distance between them? Well, to do this, we simply repeat what we did in the previous section. The distance between the two lines can be calculated using a vector projection. To calculate length using a vector projection, remember that we need two things: a vector PQ between any 2 points on the line, and a vector N, a normal to both lines. To find PQ, we can simply use given point from each vector equation at the line. Let P be 0 minus 1 and Q be 37. PQ will be just 38. Then, a normal can be found using a method previously mentioned in this video. We take the direction vector 2, 1 and swap the x value and y value, then add a negative sign to one of the values. So, vector n can be minus 1, 2. Now, we are ready to calculate the distance between L1 and L2. The distance will be the projection of PQ onto n. So this will be equal to the dot product of 3, 8 and minus 1, 2 divided by the magnitude of n. The square root of negative 1 squared plus 2 squared. In decimal form, the distance between L1 and L2 is about 9.8. As a whole, let's summarize everything we have learned. First, we learned that the mathematical definition of distance is the shortest straight path between 2 points. Next, we took a look at the different situations where distance was concerned. We learned about the distance between 2 points, the distance between 1 point and 1 lines, as well as the distance between 2 lines. However, as with everything else in mathematics, it doesn't just end there. So far, we have only covered the distance between two objects in 2 dimensions R2. What about in 3 dimensions R3? What if there are 2 lines in the 3rd dimensions, or 1 line and 1 plane or 2 planes? To find the distance in these 3 cases, there are just a few things to remember. First, the 2 objects must be parallel and distinct, or 2 skew lines. Essentially, if they are parallel and coincident or intersecting, then the distance will be 0. Second, if the distance is non-zero, then it can be calculated using the vector projection method that has been used multiple times in this video. Vector PQ joining any point on each object is projected onto vector n, a vector normal to both. The result will be the distance between the 2 objects. All in all, this is how we can work with distance in mathematics. It's not too difficult, and if enough practice is put in, then this topic shouldn't be too hard to tackle. Thanks for watching!